All right, so welcome everybody. Hopefully you had a good break, extended break. So I'll talk about confidential computing on RISC-V specific with a sort of specific focus on scaling data analytics. So I'll cover a lot of topics and I'll touch upon places where we've been working on different TGs and where things are at. Hopefully give you an idea for both like what's happened so far, what needs to happen, and where we are at in between. So yeah, we'll touch upon sort of a very quick definition of confidential computing and confidential AI. I think I've sort of introduced that topic here a couple of times. So I don't think I need to go into all the nitty-gritty details I've done in past talks. So we'll sort of move on from that, talk more about some of the specific requirements, both on compute for accelerators and for platform that want to support confidential computing and support workloads like AI specifically. And then within that, we'll touch upon ISA impacts that TGs are working on, or non-ISA impacts, both hardware, software, and then future items. So this is a sort of a popular management quality quote, right? If you can't measure it, then you can't manage it. It sort of similarly applies to security as well. If you really don't have a sense for what you're working with on your platform, and you don't have a notion of what your trusted computing base is, you really have no hope of really securing it. So, and this is not something that's new. There's a lot of security industry work that has been going on in terms of research, frameworks that are built by governments, regulations that have been deployed by governments over time. But we are like slowly reaching the point where those regulations are actually catching up and saying, hey, you need to actually pay attention not just to your data that's important when it's at rest, or when you're transporting it over networks and securing it that way, but also when it's in use, because that's critical, and that's where a lot of the system complexity issues, software attack issues, hardware attack issues can essentially lead to leakage of those data items. So data in use is becoming sort of a critical aspect, and that's really what confidential computing has been focused on for many years now. There's a consortium with a bunch of companies that have come together, hardware, software, service providers that are focused on, hey, how do we create a hardware-based TE with at least general principles, then obviously implementations across different platforms differ, but with the focus of data, protecting data in use, right? So how are folks doing it, right? Like what are the general principles that are being applied? There's a bunch of hardware-based access control mechanisms, and we'll focus on some of them that we are tackling in RISC-V in terms of supervisor domains, ISA, and things like that. There's also platform sort of mechanisms such as enforcing confidentiality and integrity mechanisms, right? Because that's important when you really look at how complex systems are today. It's not like you're processing data just within one compute environment. You're moving it out into memory, it's sitting in caches, you're moving in different classes of memory, different stages of memory, you're moving it into accelerators across high-speed buses, links, there's various interactions. But if you're successful, and actually, yeah, the third item I also want to call out is attestation, right? Like, how do you prove to somebody that you're running a particular TCB and they should rely on that? And really attestation, remote attestation or local attestation fills that gap. What are the broad implications if this is successful? If this is successful, you can actually start moving towards that notion of really measuring and managing what you have measured and enforce the TCB for that, the trusted computing base. You can control collaboration based on key data items that you want to protect while they're in use. You can comply to various regulations at like a really high degree, not just like, oh, I protected the data when it was stored. Also digital sovereignty, right? Like a lot of countries operating different countries have to deal with these regulations coming from different countries. Like, hey, this data should really be resident here. How do you prove to an entity that that data really was attached to that TCB, that container, that VM, or that workload, right? And then new business models, right? Like we've seen very interesting cases where past blockchain approaches that required complex multi-party things were really accelerated because you had a hardware-based TE that you could rely on and actually reason about from a remote attestation perspective. And a lot of those things are percolating down into network protocols and becoming sort of a normal thing to do remote attestation as part of your TLS establishment. So that really enables new things. Talking about confidential AI, like why is is that important? It's a specific workload, right? We all agree it's a workload that's of interest, but it's of high interest because the value of the AI is in the value of the model, which is attached to the model weights, and that's really critical data in use, whether you're training the model or whether you're using it for inference use cases. So, and there's various entities involved here, which is also what makes confidential computing a complex problem to solve in a holistic manner. There's a hardware provider, right, that's building the hardware. There may be additional platform integrators involved, and then there's a service provider that may or may not be present. You might be using the hardware directly, or you might go through a service provider, example, a cloud provider. Then there are entities that will act as the model owner. This might be frontier models or specific enterprise models, and you might be using services therein also to train the models. And then there's the data owner, right, which really is concerned about that sensitive data, whether it's PII, user data at a large scale, advertising data, financial data, health data, you name it, right? And they all have their requirements. And I linked a couple of papers in the bottom where you can actually go read some of these. I tried to distill them out for the audience here. Really, the requirements boil down to saying, hey, I have this such and such data. I want to associate it with this workload and make sure that it's only that workload and that TCP that I've defined that can process the data, whether it's doing model training or doing some sort of federated learning or doing inference, and where I want to keep that query private as well that's going into that platform. So yeah, there are various requirements like these model weights must remain encrypted until they are staged for use, and they should be only privy to that compute node, that compute element, or that virtual function of a device on the accelerator where my data is going to get actually operated on. And we should be able to actually verify that this data is being decrypted only by those entities. Right? So there's some cryptographic attestation or evidence associated with that. The other sort of no compromise requirement is performance should not be affected, right? If you go in and say, hey, here's a confidential computing model, but it's going to like tank your training performance by 30%, it's a non-starter, right? So it has to work across your existing compute. It has to work with groups of compute that are used together. For example, a lot of the graphics accelerators used for training have scale out links, and it should work across those groups as well. Going back to the point about measuring your TCP, you really have to ensure that you assume compromise, right? It's sort of this is like what people used to call zero trust model. You have to assume that there is compromise and reduce your TCP to least privilege. So again, this is a known principle, but it's really important in a confidential computing space. And then from a hardware provider, there are certain requirements, like any hardware, firmware, etc. that you're providing has to be cryptographically attestable through some established root of trust, right, that people agree on is trustworthy. And that really sort of pins together the requirements for hardware TEs. So confidential computing is really enabled by attestation that pulls all these properties together. So I'll go a little bit faster because I know I'm going to run out of time. So let's look at some of these building blocks for ISA and non-ISA, right? So we started with our well-loved RISC-V ISA. It has all these privilege levels already. There's Priv ISA, there's H extension, so we can run hardware virtual machines. AI and IMMU extensions have been well ratified now, right? They cover the interrupt assignment, so you can do high performance interrupt assignment, device assignment through the IMMU. The ongoing work we have is in two areas. One is on the ISA side with Supervisor Domains, which also has some non-ISA elements I'll touch upon. And then there's a bunch of ABIs or software interfaces that we are also trying to ratify under the name Confidential VM Extension or COVE. And sort of a play on, like if you've heard of other terms that other architectures use, like enclaves or realms, this is a COVE, right? So hence the name. So Supervisor Domain essentially gives us this new capability of like taking the well-known supervisor context that we have, whether you look at it as a virtualized or non-virtualized, and lets you start creating alternate supervisor domains or supervisor contexts, right? One of the key values of that is it lets us preserve a lot of the ISA work that has happened, right? And reuse a lot of that without adding special functions into every ISA extension that we define in the future, right? So once things are contained within a new entity called TVM here and managed by a new entity called TSM or a TE security manager, which essentially again runs in the corresponding privilege context, supervisor or hypervisor plus supervisor, right? Enabled through a root TCP layer, right? So your TCP path sort of is your hardware with the root of trust, your firmware TCB, a TSM to sort of manage workload separation here, and then the TVM. So from a TVM perspective, that's really your trust path, right? And you want to restrict your workload within this TVM with only that TCB, and none of the things around it matter, right? That's sort of the goal of supervisor domains. So if you have a host hypervisor, you have other VMs, ordinary VMs running on the side, or even other trusted VMs running on the side, they're all outside your TCB, right? So that's the whole notion of like managing your trust computing base. This is sort of like a big picture of like what supervisor domains look like, right? Again, like I said, we maintain a lot of the existing execution context and we wrap it in an additional execution context called the supervisor domain ID, right? So one of the very basic parts of the extension in supervisor domain is this SMS SDID, which basically gives you a notion of like tagging caches, etc., address translation caches with this new SDID context, right? And the implementations are allowed to be flexible in terms of how wide of a SDID namespace it supports. The second aspect from the ISA perspective is providing physical memory isolation, right? So that's an important sort of capability we want to provide where once you have a supervisor domain, let's say you have like a hosting supervisor domain where you boot up the system through secure boot, it's managing all the system memory, and then it assigns memory or donates memory to secondary supervisor domains. Through this SMMPT interface, the RDSM can enforce that once that memory is donated, it's really not accessible to the host domain at all, right? And going beyond sort of where we were at with PMPs in the past, right? Where we can do this more flexibly, compose it very well with SV so that you can do it at all the architectural page sizes and support rich OSs running in the supervisor domain environment, right? So you can flexibly move memory between these supervisor domains. And then there are a few other extensions that build on top of that for doing interrupt assignment securely as well. This is sort of like a logical view of the memory protection tables that were introduced as part of supervisor domains. And essentially, we want to basically have a very consistent access control model, whether access is coming from a device side access through DMA, or it's coming from the CPU side. And again, still composing well with the existing Priv ISA first stage and the G stage page tables. Similarly, composing very well with the IOMMU definition, right? So that we are not asking hardware designers to change how they've implemented IOMMUs and things like that, but essentially give them extensions that allow them to use that functionality and build on top of that. Let's switch gears a little bit to accelerator requirements. So when in this same picture, if you recall from before, if I add an accelerator, it sort of brings in these other entities into the mix, right? So you have an accelerator on the bottom. I'm calling it a device or an accelerator which is TEIO capable, right? So what does TEIO capable mean? So in the broader industry, that term TEIO capable is basically associated with a set of protocols, right? And I apologize for not writing the acronyms here, but SPDM is a DMTF protocol for secure protocol data model. It essentially gives you a packet format that can run over different buses, and it allows you to essentially authenticate a device, right? Which is the first thing you need to do to validate that the device is actually coming from a trusted source before you actually start interfacing with it, right? The second one is IDE. This is standardized by the PCIe forum, PCIe SIG. It stands for integrity and data encryption, and the dash is for key management. It's basically a protocol that enforces, as the name suggests, integrity and data protection through ESGCM between your CPU complex and the accelerator complex, right? So you enforce that the links that are leaving the platform where somebody can put in an interposer are not observable by an attacker, right? And then the third one is TDISP, which is basically a TE device interface security protocol, also standardized by the PCIe SIG, but it was heavily sort of built for this sort of capability where once you have a device that you've authenticated and you have created a secure link between the host complex and the device complex, how do you actually give the device an interface so that when a TVM is managing the device and getting ready to send its data to the device, it has a set of verbs that it can manage the state of the device, right? Because you want to prevent all kinds of weird system time of check, time of use attacks to say, hey, I'm getting ready to program this device to do DMA. Is everything set up for me to start using it, right? So TDISP basically gives you that verb. So just expanding it on a little bit, like I said, we don't modify the IMMU for use with confidential computing. We basically suggest a model such as this, where you essentially take the same IMMU interface, you use the notion of access controlled or confidential memory, and you place your IMMU data structures for use by data traffic for TE that is destined for TE memory, or data traffic that's destined for non-TE memory. And what you see on the top there is as packets come in through the bus interface, in this case PCIe, it has this T-bit on it that lets you essentially demux your access and lookup into either a trusted set of page tables for the IMMU or an untrusted set of page tables, right? Thereby, you can reach the right context that you want to reach when you perform that the DMA from the device perspective. The remaining part that we added in the supervisor domains is to basically make sure that there is an IO MPT checker that's shown here that has a couple of interfaces. One, to basically take an inbound transaction and map it to a corresponding supervisor domain and IOMMU, so that you know what MPT structure to use, and in the context of that supervisor domain, what IOMMU is assigned to that supervisor domain. And from that point on, your page walk essentially proceeds as normal with your physical entries of the page physical addresses going through the MPT lookups. Right? So that gives us that sort of consistent access scheme that we were looking at earlier. A little bit on the software ABIs. This is work that's ongoing in two split TGs, the Cove and the Cove IO TGs. Right? They basically give us interfaces so that we can dovetail into the open source work that's going on in this space. Again, we want to kind of reuse the work that has already happened in open source for other architectures. So this ABI gives us a RISC-V specific mapping to take those common interfaces built in Linux and map it to our architecture, to the RISC-V architecture. I'm going to skip this slide because I don't have that much time. But this is sort of a high-level bird's view on like what the Cove ABI does for memory management. Right? There's also a similar set of ABIs extended for Cove IO that essentially give you a set of verbs that let you bind a device interface to a confidential VM. And once that confidential VM is bound to the device, the data path that's shown in the dark blue basically means that those data accesses are not going through any other bounds buffers or anything like that. There's no software encryption involved. All the data access is basically being done through the hardware paths that are sped up through address translation caches and memory encryption. Last but not the least, a lot of these standards that we're creating, whether they're ISA or protocol standards, they really rely on an ROT, right? So we've done a lot of work on OpenTitan as an ROT engine. That's all based on open source silicon. So you can go look at OpenTitan, hardware root of trust. You can look at all the IP elements of it. We've added a bunch of key IPs there that really prepare a platform for doing things like confidential computing, where you can support a dice protection model for different identity chains. You can support an attestation model that's standards compliant and so on. So I would encourage people to take a look at these as a key capability to use in your platforms. So this is my last slide, just a status of quick ongoing work. So on the ISA side, we basically completed most of our ARC review feedback so far, and really big thanks to the ARC community for helping us with those reviews. The Cove spec was paused a little bit while we finished our supervisor domains ISA work. Now we will kind of turn our attention back to that and complete the ARC review for that. In parallel, we have a QMU prototype for supervisor domains that's ongoing. We have a TSM implementation we had started some years back that we will clean up. And really the pending items for us are the SAIL and ECT work that we need to do. And then from that point on, the next logical step is taking some of the patches upstream into Linux KVM. Again, some of that work has already started, but once we finish our Cove ABI work, we can sort of focus on that in earnest. So with that, I'll end here. Sorry for going a bit over time.
This is more on Cove and the ABIs. So we've seen now that Cove has its own ABI, and this is for handling confidential payloads, so confidential VMs. We saw earlier the way OPT porting on RISC-V is going, which is a completely orthogonal direction. So we are seeing in RISC-V the same dichotomy that happened on ARM happening also. And coming from there, it's like, it feels like a missed opportunity. So actually both the works are being discussed in the RISE work group, right? And we recognize that some of the platform requirements are different for those two environments. Like OPT is primarily based on what ISA we have right now and is restricted to
those embedded use cases with PMP, right? We have talked about sort of Opti also being supported in data center-like workloads, right? Where we can sort of use some of the new ISA capability, which we need for those platforms. There's a similar discussion going on with PKVM folks as well, right? We want to avoid the same sort of mistakes that happened on ARM-CCA, where PKVM went one route and ARM-CCA enabling went a different route. So yeah, that's actually an active work group item in the security work group in RISE. So you're welcome to join in, because we are explicitly trying to make sure like we have one Cove ABI that we are using as the common interface, and have all these like higher level APIs, whether it's the Cove or like Linux KVM, what they're doing for other architectures, use those common APIs. Right? It also helps us from a security perspective, because if we can reason about TSM as a standalone thing, we can also reason about its security properties, do formal verification, things like that, right? And I think Andy had mentioned like we want to do the same for like the RDSM layer as well. That's like your root M mode firmware layer that's doing context switching and things like that. We want to make that sort of reach a point where it's sort of a clean Rust implementation. There's a standard interface and a standard reference implementation that people can look at for formal and other such evaluations.
We're out of time. Let's thank the speaker.